JNV Ujjain, I can see people sitting there, but for everyone else, the videos are switched off. So it would be really great if you can switch on your videos. Okay, like Justy already talked about. I mean, that was some introduction about me. So I've been doing a lot of things for past 15 years, and the one thing that I've enjoyed the most is teaching. So whenever I am in a classroom and discussing stuff which I've learned from various uh, endeavors of mine, I feel the best. I mean, that is the best feeling that one can have. And I think I should thank America India Foundation, Justly, everyone for this opportunity. So today we thank you so much for this opportunity. Thank you so much for joining us, CCL IIT Gandhinagar. I'm really grateful on behalf of CCL IIT Gandhinagar that you guys have joined. So today the session is on optics. Basically the session is on light and how light behaves. What are the various phenomena that light, you observe with light. So we would start with the very basic questions. I mean, very fundamental questions. So I would like you to, so let me just share the learning goals first. And so then, see, the learning goals are like these. I mean, we would like to understand that how do we know that light travels in a straight line? And we would also, if there is that, if this is a fact, then can you use this fact that light travels in a straight line to have some fun? So we'll see if we can make something interesting to create some fun out of it. And now maybe light does not travel in straight line. It bends. Then if it does bend and if it does not travel in straight line, then how do we know? Matlab, if it travels in straight line, there must be some reason. If it doesn't, then there also must be some reason. Kuch to experiment kiya hoga, there must be some observation. And then we'll talk about diffraction. So the moment I talk about diffraction, I think a lot of people must have understood that the conclusion to the above debate is that light maybe is not traveling in straight line. And then we'll talk about other questions like why sky blue, why are clouds white, and various other things that we can use, where we can use diffraction to figure out stuff. So these are, to figure out stuff around us. So these are our basic learning goals. Now I would like to start with asking a question. How many of you believe that light travels in a straight line? How many of you believe? If you believe that light travels in a straight line, you can just raise your hand. Can you see the hand? Light travels in straight line. If you believe, you don't have to do this. Or you just have to raise your hand. So if you believe that light travels in straight line, then okay. So light travels in straight line. A lot of us believe that light travels in straight line, which means that is the only option that light has, or there are other options. When light light is pretty moody, can change the path whenever it wishes to, but usually it travels in straight line. What do you think? It is always that light travels in straight line? Is it always traveling in straight line? Can you raise hands? Show of hands. Okay. So Aristotle. So let me take you to Aristotle. So Aristotle believed that light does not travel in straight line. Aristotle had his doubts, and I'll just show you what was the basis of Aristotle's doubt. So let me show you the basis of Aristotle's doubt. So can you see this picture? Can you see the picture? Is the picture visible? Does light travel in a straight line? Aristotle's argument. Can you see this presentation? Yes? Can you raise hands? Okay, I think it is. Okay, so what Aristotle was saying is that if, light travels in a straight line, and if you have a slot like this, so there is a rectangular slot. Can you see this rectangular slot? And then if light, travels in straight line, then the image that you get of this rectangular slot should also be rectangular. So let's say if there is sun is the source of the light, and the light is passing through an opening, then the resulting image should resemble the opening and not the luminous body. That is what Aristotle's argument was. If it is traveling in straight line, then this is what should happen. And what he realized was that when he was watching solar eclipses using pinholes, he was actually able to see sun, which is the luminous body, and not, the image was of the sun and not of the of the opening. Does that make sense? Does that make sense? Did you understand the argument? So let me demo this argument. So here we have, I'll just show you. Yeah, so this is a piece of paper and all of you can do this together. So what you need is just a piece of paper. If you have a piece of paper, we can all try doing this together. So what we need is a piece of paper, and then you have to create some holes in this piece of paper. So as you can see, I have created a triangle, and then these are two diamonds, or maybe you can call them squares, whichever way you look at them. So if you have pieces, if you have a piece of paper, can you just create quickly these triangles and squares? And then what you have to do is, you have to see how their image looks like. Can you see? These are the images that I'm talking about. So for a triangle, I can see a triangle. For a diamond, I can see a diamond. For another diamond, I can see a diamond. But what happens when you bring them a little away? I mean, when you take them a little away from the screen, you would see that the shapes have become dissolved. I mean, they have become distorted. And in fact, over here we have a lot of light sources. If in your case, if you just have only one light source, then then what you will see is that this image now, the image now would resemble the shape of the luminous object, right? So what was Aristotle's argument? Aristotle's argument was, let me take you back to the Aristotle's argument. Where is cursor? Okay. So Aristotle's argument was that if light travels in straight line, then of course all the time, whatever the distance might be from the screen, you should always see the image as, you know, the opening. The image should resemble the opening. It should not resemble the luminous body. But we have seen solar eclipses using pinhole cameras. We have seen, we have just done a demo, and we know that it doesn't happen. It doesn't happen. Sometimes it does, sometimes it doesn't. So then, can somebody explain what is happening over here? I'll just give you a hint. When I take it just slightly away, what I'm seeing is, let me just show you this a little close. Echo is subcomputer. Okay. So what happens is that if I take this slightly away, just slightly away, then you would start seeing that instead of one triangle, now you have multiple triangles. Can you see that? Or multiple diamonds. This is one triangle. थोड़ा सा ऊपर ले जाओ तो थोड़े और diamonds लग जाएंगे, थोड़ा और. So that's what is happening. Now this is a hint. Can somebody answer? Can somebody tell me? कोई बता सकता है कि हो क्या रहा है? Does light travel in straight line, or Aristotle was right? Can somebody explain this? You can answer in comments. I can just read the comments. Is there anybody who is answering in comments? Let me check. So let me just reiterate the argument. Aristotle said that if light travels in straight line, then for any object, you would see the image should resemble the opening. Opening जैसा है, opening triangle है तो image भी triangle होना चाहिए. Opening rectangle है तो image भी rectangle होना चाहिए. पर हम लोगों ने क्या देखा है कि if the screen is very close, तो ऐसा होता है. If the screen is very close to the object, but if you take the screen away, screen को दूर ले जाओ. ये तुम्हारे objects हैं और ये screen है. If you take it away, if you take it away, then what happens is that now what you're seeing is the luminous body. So if you do this, this would be really interesting. If you have a tube light overhead, then you would start seeing a tube light. If you have let's say a very round sort of light, then you'll start seeing the round light. And if you have some other fancy table lamp, then you will start seeing the table lamp. And you can have these pinholes could be very small. I mean, if they are smaller, the effect would be even more apparent. You can try doing this. This is really interesting. So this, confuses us, because if light travels in straight line, that should not happen. Then what happened? That people were able to convince Aristotle that no, Aristotle, you are not right. And they gave him an argument. They said that, see, this is what is happening. So you are assuming that the object is a point source, while that is not the case. The object is not a point source. It is actually a very large object. The luminous body is a very large body, and hence a lot of a lot of images are being formed. So as you can see over here, and I'm not getting into details of this, but I would just repeat the entire thing using the mobile flashlight, and we will be able to understand what I'm trying to say. So what is Aristotle saying, or what is the other people who are trying to argue with Aristotle? They are saying that, see, you have an object which is not point object, which is actually a larger object. It is not a point object, right? Does that make sense? Do you understand the difference between a point object and an object which is not a point object? एक बिल्कुल छोटा सा बिंदु जिससे बहुत सारी लाइट रेज निकल रही हैं, और if there is an extended object जहां से बहुत सारे छोटे छोटे points हैं and the light rays are you are able to see multiple sources of. So basically one object has multiple sources of light. Then when you draw these ray diagrams, you would see that you would get multiple images. These are the images that I'm talking about. ये देखो एक square, ये दूसरा square, ये तीसरा चौथा, and there are so many squares that you form. And because there are these all squares are being formed by multiple parts of the source, that's why they all together make the source. If you are very close, to the screen, then they would overlap. They would overlap and they would resemble the hole or the opening. But if you are a little away, then they would resemble the larger, the luminous body. Does this make sense? Could anybody understand this? Now let me just repeat the same thing with a flashlight or with a mobile flashlight. Where is my mobile? Yeah. So let me just do the same thing. Now I have a mobile flashlight, right? So let me show you what happens now. So now, as you can see, even if I take it away, is it visible? So even if I take it away, the shape is still more or less there. Let me just show you. Can you see? The shapes are still there. Why is this happening? This time, this is much. So this time I have my entire thing much higher. I mean, this is now much further away from the screen. So this is my screen. These are my objects, and this is my light source. Can you see the light source? This is the light source. But the light source is a point object. So now if you see, even when they are far away from the screen, it has images which resemble the opening. अभी opening जैसा ही image दिख रहा है, right? Opening जैसा ही image दिख रहा है. क्यों? क्योंकि अभी मेरे पास point source है. Point source हटा दो, सब बिल्कुल you stop seeing that. वो distort हो जाता है. The image becomes distorted. Then you are getting multiple images, and all those images actually mix into each other, and it doesn't work. So why I am discussing this story with you? Anybody? Why are we discussing this story? Why are we discussing this story? Okay, so we are discussing this story because this is how science works. People will give an argument. They will say, "Arey, light doesn't travel in a straight line. How do you explain light traveling in a straight line when such a thing is happening?" Then somebody will come an argument and say that no, light does travel in straight line. What you are ignoring is the fact that the luminous body itself is, large in size, and it has multiple smaller luminous point objects, and all of them are making images, and they are overlapping, and that is why you are seeing the shape of the luminous body. And then somebody else would come up with another argument, and this back and forth keeps happening. And has it stopped today? Are we convinced about the nature of light today? Not even today we are convinced. This back and forth is what science is. You say something, I come up with an experiment to prove you or disprove you. All the time what we are doing in scientific method is, there is a theory, there is a hypothesis, and we're trying to prove it wrong. So Aristotle said that light does not travel in straight line. I'm now designing an experiment to prove it wrong. Or if I have a theory which says that light does travel in straight line, and Aristotle designs an experiment that proves me wrong, I give a better explanation. Telling that, see, an extended object, even with light traveling straight line can have whatever you are observing. Right? That's what science is all about. That's what science is all about. Science is not knowing facts. Science is not just knowing whether light travels in straight line or not. Science is about this back and forth. You keep discussing things, you keep giving hypotheses, you keep testing them with experiments, and that's the fun part. I mean, that's the fun part. The fun part is not solving numericals. The fun part is doing these experiments and then arguing based on whatever, data you have. Okay. So let me just quickly take you to okay. So I'll just show you now. I mean, maybe more or less we are convinced that light travels in straight line. ठीक है, हो सकता है light travel straight line में ही करता है. A lot of you were already saying that light travels in straight line. I'm seeing majority must be right. So let's just use the fact that light travels in straight line and design something funny. Design something interesting. So I'll just show you a video. This is a pinhole camera that we designed. This is called a cross slit camera. It's a camera that we designed in our lab, and I'll quickly show how does it work. Let me play.
हमने अपने लैब में ये नया पिनहोल कैमरा बनाया है. आइए देखते हैं कि खास किस तरह से है. इस पिनहोल कैमरा में बाहर एक हॉरिजॉन्टल स्लिट है, अंदर एक वर्टिकल स्लिट है और इस तरफ हमने एक स्क्रीन लगाया हुआ है. अब हम इस पिनहोल कैमरा से अपने लाल मीनार को देखने की कोशिश करते हैं. इस पिनहोल कैमरा में हम किसी भी एक एक्सिस एक्स या वाई एक्सिस में इमेज को मैग्नीफाई कर सकते हैं. क्या बता सकते हैं हमने कैसे किया?
So what did you just see? There was a pinhole camera. This is the diagram of that pinhole camera. There are two slits. One is horizontal, another is vertical. And what you are seeing is that you are able to distort the image. Image distort हो गया ना? वो लाल मीनार, that's a very iconic building in IIT Gandhinagar. The image got distorted. कभी वो it got magnified in the horizontal direction. कभी it got magnified in the vertical direction. So it's basically you can do it with people. You can make their faces funny. You can draw caricatures of them. किसी को थोड़ा मोटा कर दो, किसी को थोड़ा पतला कर दो. You can do that using this very simple pinhole camera. कुछ नहीं है, दो slits हैं और slits को आगे पीछे कर रहे हैं. Why is that happening? This is happening because we have used the fact that light travels in straight line, and now what is happening is, if you can just quickly, if I can explain what is happening over here is, see, there are two slits. One of the slit is horizontal, another slit is vertical. Now this horizontal slit is taking care of all the light that is coming from the vertical part. If the horizontal, if you have a thinner horizontal, if the horizontal slit comes closer, this is the horizontal slit. If the horizontal slit comes closer to the object, then this light, after passing through the horizontal slit, will have to travel further. और ज़्यादा travel करना पड़ेगा. मतलब the vertical part is going to get magnified. So ironically, or very interestingly, horizontal slit से depend करता है कि vertical portion कितना magnify होगा. If you bring the horizontal portion further away, if you take it further away from the screen, A is the screen, C is the horizontal slit, C वाले portion को थोड़ा दूर ले जाओ. दूर ले जाने का मतलब C को D की तरफ ले जाओ. If you bring C towards D, then you would have this vertical part of this plus. This plus is our original object and this plus is our image. If you bring it closer to the D, then what you would see is that what would happen if it goes closer to the D? That this gets magnified. A gets magnified. In this entire thing, this is magnified because it is magnified vertically because C is relatively closer than B. B screen से ज़्यादा पास है, C screen से ज़्यादा दूर है. You must be knowing this. Projectors you must have used. If the projectors are away from the screen, the images are larger, right? So same is happening over here. ये जो hole है, it is responsible for projecting the vertical part of the image. जितना ज़्यादा hole को दूर ले जाओगे, the further away the hole is from the screen, the further away C is from A, the larger the size of A is. Does this make sense? So it's a very interesting toy. I'm pretty sure, if you make it, if you, play with it, it is very important, easy to make. What do you need? Just a piece of chart paper, and then you need to create two slits, just two slits, and then a butter paper to act as a screen. And if you can create it, and I mean, we will have, there are some details already on our website. You can actually, if you want, we can share more details. if you create such toys, you would really enjoy, the fact that so far you were just aware of the fact that light travels in straight line. If you have this understanding, then you can make interesting entertainment oriented things using the facts that you are aware of. So it is not just mere knowledge. Now you can actually apply it, and apply it for fun. I mean, why just apply it for solving problems of world? Maybe you can just do some fun activities, and you can just apply them. Okay, so abhi tak light travels in straight line, that part is winning. So let me show you another demonstration. And here is our another demonstration. Let me take you to our another demonstration and let me show you. Okay, so what you're seeing over here is, this is just a pair of scissors and this is a flashlight. Abhi what we are going to do is, we are going to put the edge of the pair of scissors in front of the flashlight. And then what do you see? So did you notice there are colorful bands? So of course we were expecting that you would get shadow. कोई भी object को if you put in front of a light source, you would see shadows. But यहाँ पर there are just not shadows. I mean, instead, there is a shadow of course, but there are these colorful bands which are around the shadow, which are just adjacent to the shadow, the edge of the shadow. And we will repeat the same experiment with the. So we'll repeat the same experiment with a razor blade as well, and then you can check what is happening over here. Even with the blade, as you can see, there are these bands which maybe are not very clearly visible because of the resolution, but there are these bands. Even with the blade, you would see that these bands are visible. So Grimaldi was a scientist who first observed it. He was a professor of mathematics in, I think in Italy, and he realized that the size of the shadow. So geometrically, when we create shadows, what do? We just draw a straight line, and then wherever that straight line meets the screen, udhar shadow bana dete hain. I'm pretty sure some of you who must have done some drawing, you know how to create shadows. Ek object banao, and so let me just show you using an overhead. What you have to do is, you have to just create an object ऐसे, and then you create a plane ऐसा कुछ करके है. Then you can create a 3-dimensional object इस तरह से. Then you just draw a line, right? ऐसे करके एक line draw करते हैं, and then you make it. So ultimately what you're doing is, you're just joining the line that is considered to be the line which is the straight line motion of the light, and it just touches the edge of your object, and then it joins the plane on which the shadow is being formed. And using that, you figure out कि भाई तुम्हारा shadow, where is it starting from, or what are the coordinates of your shadows. That's how you do it, right? So I'm not getting into the details of it, but then the larger point is कि every time whenever we draw shadows in a drawing class, or if you're doing engineering drawing or something similar, you assume that light is traveling in a straight line. But Grimaldi was able to see, Grimaldi ने देखा कि यार नहीं, it is not that the case is a little different. He observed that the size of the shadow was much larger. The size of the shadow was much larger than the shadow that you would draw using this geometrical optics. I mean, straight lines draw करके जो shadow बनता है, the actual shadow is much larger than that. Right? Isn't it amazing? I mean, all our life, all our painters, all our whatever, Picassos and whoever they were, whenever they were drawing shadows, they were using this technique, just draw a straight line from the source and then make it fall on the surface, and that point is the point where your shadow ends, and using that they can find out, the points of the shadows, and they can just join them and create a shadow. So they can do that very easily. They have been doing it for so many years. But then Grimaldi, when he did a few more observations, he realized ऐसा तो है ही नहीं. Shadow तो थोड़ा सा बड़ा है. या कभी-कभी, in some cases, it is even slightly smaller. So what does that mean? That means that light maybe is not traveling in straight line. And if light is not traveling in straight line, what is it doing then? So I'll just quickly show you another demo. So this is a very simple setup. What we have done is we have taken a laser. Always be very careful when you are using lasers. Then we have taken a convex lens just to ensure that the laser gets a little spread out. And then finally this convex lens, is making a huge ultimate. And then we are placing a razor blade in front of this this beam. So this is a monochromatic light falling on this screen, and then what we have done is we have put a laser beam. Abhi, if you see carefully, now if you pay attention, you would see that there are very interesting lines around the edges. Just look carefully, you would see that there are a lot of interesting lines. So you would see a bright line, then a dark line, then a bright line, then a dark line around the edge. I'll just pause where it becomes more apparent. So if you see over here, if you see, this is a darker line, this is a brighter line. Right next to the edge there is a brighter line, then there is a darker line, then there is another brighter line. And this is a very easy experiment to perform. Of course, because you are using a laser, you should do it in a little supervision. But it's a very simple experiment to perform, and you can see that the shadow has something very interesting happening around it. I mean, you can see these are called fringes, right? You must have read about these dark fringes in interference and diffraction in your grade 12th. So these fringes are even seen. These fringes are even seen when you are seeing the shadow of an object which has sharp edges, and the shadow is because of a monochromatic light. Abhi monochromatic light hai, so what you do is you get dark and bright fringes. If it is not monochromatic, if it is white light, then you get bands of colors, then you get multiple colors. And this can all be explained using a phenomena called diffraction. Diffraction you might be aware of, and we would not get into the boring definition of diffraction. But diffraction basically is because of the fact that light behaves like a wave. It behaves like a wave. And since it is behaving like a wave, that is why, and also we know that white light is made up of multiple wavelengths, right? It is not made up of just one single wavelength, it has multiple wavelengths. So there are some wavelengths which are going to constructively interfere at particular point. There are some wavelengths which are going to constructively interfere at another point. So कुछ कहीं constructively interfere करेंगी, कुछ कहीं. So when you have white light, you have a band of light, and that is because blue is constructively interfering here, green is here, red is here, and so on and so forth. But when you have just one monochromatic light, then there are points where they would constructively interfere. What do we mean by constructive interference? When the waves have superimposed crest on crest and valleys on valleys. So when they have superimposed like that, that would mean that there is a constructive interference, which is that ultimately what you are getting is that you are getting a superimposition. But there is also possibility of crest on valleys. This can also happen. This is called destructive interference, right? You must be aware of it. So the point is that this was so. How did we come to this? How did we realize that diffraction, history, what is the history of diffraction? How did people started thinking about the fact that light does not travel in straight line? For almost 1700 years of the scientific revolution, or whatever, of the science, and even more than that, for around 2000 years of scientific history, we believe that light travels in straight line. बहुत मुश्किल था ये observe करना. It took a lot of effort. Some people might have paid a lot of attention to this, and then they realized that it is, something interesting that is happening. And a lot of people started arguing for the fact that light does not travel in straight line. Light actually behaves like wave. So then I'll just take you to an argument which happened back then. And this is how science progresses. So, yeah, I think I need to put myself in spotlight. Let me do that. Okay. So, yes. So there was this famous story. What happened was that there was a competition organized by French Academy of Sciences in 1819, where people were supposed to give their argument that they were supposed to explain what is light doing? Is it a wave or is it moving in straight line? And there was Fresnel, a French scientist. He said that light travels as wave. He has seen all these phenomena before, and he was saying that they can all be explained if light travels in wave. Then Poisson, one of the jury member, said that this is such an absurd idea. It's such an absurd idea that if that is the case, then you should get a bright spot right at the center. Do you understand what is happening over here? It is such an absurd idea. He saying कि इतना बकवास आइडिया है भाई कि अगर ऐसा होगा तो इसका मतलब है कि शैडो के ठीक सेंटर में तुमको एक ब्राइट स्पॉट मिलना चाहिए. वी हैव ऑल सीन शैडोज. शैडो के बीच में कहीं कोई ब्राइट स्पॉट होता है क्या? हार्डली एनीबडी मस्ट हैव सीन इट. So shadow के बीच में there is hardly, I mean nobody has ever seen a bright spot right at the center of a shadow. But Poisson said that इतना ऐसा तो कभी होता ही नहीं है because nobody has ever seen it. So अगर तुम्हारा केस सही है, if light is behaving like waves and diffraction is happening, then right at the center you should get a bright spot. As if there is no object. वहाँ पे object है ही नहीं, जैसे object में खोल कर दिया हो. This experiment was actually performed by a French physicist Arago, and the spot was seen. They were able to see the spot. So imagine there is an object, उस पर light डाला है, उसका शैडो दिख रहा है. So there is an object. I'll just show you. We have that object with us. Yes. So this is, let's say this is yeah. So you can see this is a ball bearing. बहुत ही smooth है and it's perfectly spherical. It has to be smooth and spherical. नहीं तो वो bearing की तरह काम नहीं करेगा. तो friction हो जाएगा और दिक्कत आ जाएगी बाकी सारी. So we use this object. I mean, the same experiment we also performed in our lab. हमने भी किया अपने lab में, and we saw the same Arago spot or Poisson spot as it is called. So what is the point? That आपने एक object लिया, solid object है, उस पे light मारा, उसका shadow दिखना चाहिए, दिख रहा है. But right at the center of the shadow, what are you seeing? You are seeing another bright spot. I mean, can you believe it? That एक shadow के ठीक बीच में you have a bright spot. How is that possible? That is possible if light behaves like wave and if there is diffraction. So let me just show you that setup. Okay, let me show you our setup where we did it, and it is again very easy to perform. So you can see for yourself. So what is it? We have a laser, and then in front of it there is a convex lens. It's a magnifying glass, which is a convex lens, which is basically making the beam a little broader, I mean thicker. So then finally this beam spreads out and it falls on this object. Can you see this? It falls on this object. So object पे अभी वो red light गिर रहा है. And then when you see this final image, can you see this bright spot right at the center? Isn't this amazing? Right at the center there is a bright spot, and this is happening because light travels like a wave. Now the why are we, I mean, again and again discussing the fact that whether light travels like a wave or it travels like a straight line? That is because I want you to appreciate, and I mean it is so interesting how things happen, and this does not happen immediately. ऐसा नहीं है कि ये किसी के दिमाग में 1600 में एक किसी ने ऑब्जर्वेशन किया and within a few months you were like done and everybody knew that light always also behaves like a wave. It took so many trials, so many experiments, this back and forth kept happening, and ultimately they did these experiments. बहुत time लगा उन लोगों को initially. So the first time when Arago did the experiment, this experiment he did not have a laser. उसके पास laser था ही नहीं. He did not have a laser. I didn't know. So it is very difficult to reconstruct Arago's experiment. It is, I'm not aware. I mean, how did Arago did it? How he could create that spot at the center of the shadow. So it took a lot of effort in those years, but they kept doing it. This argument kept happening, and ultimately they could prove that yes, light travels like a wave. And which is why a lot of things that we see today, the fact that you're seeing me, the fact that I'm seeing you, is because we are clear with our concept that light or any electromagnetic radiation is a wave. Otherwise, all this electromagnetic communication is not possible. So all that back and forth happened long back, and it took a lot of effort. But I want you to appreciate this journey of scientific endeavor. Okay. So is are you able to understand? I mean, is it making sense? Okay, I'm struggling with my cursor. Why the cursor is not able to move up? Let me check. Oh yes, I'm getting it. Okay, now, so when I was a student like you, I had a great difficulty in understanding diffraction. Because diffraction was very difficult to perform. अभी स्कूल के अंदर hardly any time we were able to perform diffraction. हमको diffraction करने को ही नहीं मिलता था या होता ही नहीं था, because mostly when you are doing diffraction you would need gratings. You would need something like this. I'll just show. If you want to do diffraction, you would need a grating, something like this. Can you see? This is called a diffraction grating. So basically it's a glass plate where you have very, very thin lines. So this says that it has around how many lines? 15,000 lines per inch. 1 inch has 15,000 dark lines. So they are so thin that you are not even able to see them. But you have 15,000 lines per inch, मतलब बहुत सारा lines डाल दिए एक के बाद एक, and बीच में spaces भी हैं. And which is why you are able to see through, नहीं तो फिर ऐसे दिखता. And this is called a diffraction grating. These are expensive, not very, not very affordable, but then not very expensive as well. So ये diffraction gratings were required to do diffraction, and फिर वही था कि भाई lab में कौन diffraction grating बच्चों को दे और बच्चे तोड़ देंगे. So all that stuff, and then ultimately diffraction never happened in our lab. Maybe it happened once or twice. Sir gave a demo, and then it went away. So what we have done at CCL is we have tried out various day-to-day objects which can be used to create diffraction. So we have tried that using recreating diffraction using feathers. We have tried recreating diffraction using razor blades and a lot of other things. So I'll just quickly show one of our video where we tried seeing diffraction using a feather, and you can do this. This is very simple. Let me just show you what did we observe.
यो
कल जो देख रहा था वो ये था।
इसमें बढ़िया आया।
So can you see this rainbow effect? And that can be explained using diffraction. And this is exactly what you are seeing. Because you are seeing white light, तो इसलिए तुमको वो rainbow effect दिख रहा है. If you are seeing a monochromatic light, then you will see bright and dark fringes. So here is another experiment. So abhi, now the problem with this demonstration is you should not try this, because what you are doing is you are actually straight looking into the sun, which is not advisable. Do not do that. That's not good for your eyes. So please don't do that. We did it with very utmost care, but as a student you should not do it. But you can do a very simpler experiment, and let me tell you how to perform that. It's pretty simple. You just have to use your mobile flashlight and then the same feather, and you would see similar bright colors or rainbow effect with just the flash of your mobile flashlight. Can you see the colors over here? Can you see some colors at the top? Again, very easy to perform. बहुत ही आसान है करना, बस एक flashlight चाहिए setup के अंदर, and then you need a feather. And this is with white light. So let me show you what happens when you have a monochromatic light. मतलब same single color है, तो क्या होगा? So feather चाहिए और एक बस वो source of light चाहिए. That is it. Nothing else is required. So you have a feather. This is how our feather looks like. And then this is our laser beam. This is not laser. I mean, initially we switched on the normal light. This is the laser, yeah. So this is the laser beam. Abhi now you have to shine this laser beam through the feather. So when you do that, what happens is, let me show you. Yes. So this is what you see on the screen. Can you see a bright spot, then a dark fringe, and then again a bright spot, and so on and so forth? So diffraction, this is because of diffraction. I'm pretty sure a lot of you must be aware of it. So diffraction is something that you can very easily see using just a feather. I mean, another reason to go out and observe nature and have fun. I mean, a lot of people now just are hooked to their smartphones and iPads and whatnot. But go out, collect some feathers, figure out which feather shows you the best diffraction. All you need is a flashlight. If you have some adult supervision, you can also do it with the sunlight as well. Okay. Now, if you do not have a feather, which is very unlikely, but let's say if you don't have a feather, then you can also do it using razor blades. So let me show you. So again, a simple setup, very easy to do. These are just two razor blades. I'll show you this, how we arrange these razor blades, and they are very close to each other, and then the laser shines through the opening between them, and you can see on the right of your screen how is the diffraction pattern when the blades are vertical. When the blades are vertical, the diffraction pattern is horizontal. And if I rotate them, let me rotate them. So now the slit is horizontal. The slit because of the blades is horizontal, but the diffraction pattern is vertical. Very interesting observation. You can try this very easily. Right? Now let me just show you this. So this is our setup. This is how simple it is to make. I mean, kya hai? Gatte ka tukda. This is just a cardboard, and these are two blades, and this is the slit that we are creating. So you have to just ensure that these two things are pretty close to each other. You can try different openings, and it is done. That's it. That's what you need. In fact, you can use something like a vernier caliper. If you have a vernier caliper in your lab, so this is a vernier caliper. I'm sure you must have seen a vernier caliper. So if you have a vernier caliper in your lab, then you can just, यहाँ पर तो vernier caliper makes it so simple because this screen gives you a reading. It tells you how far away these jaws are. They can, you can figure out whether it is a micrometer away or a millimeter away or whatever. The screen, this can give you a reading. You can read it and you can find out कि ये दो jaws हैं, इनके बीच में distance कितना है. So जो तुम्हारा slit का size है वो तुम निकाल सकते हो. और फिर यहाँ पे you can shine laser. You can shine a laser over here and you can see the diffraction pattern on the screen. So, I mean, so simple. I mean, you don't need a grating. You can also do it using a CD, a compact disc. Can you see the colors in this disc? Can you see the colors, the rainbow effect in the disc as well? This is because this disc is also nothing but a diffraction grating. This compact disc is also nothing but a diffraction grating. Why? Because CDs, the way CDs work is they have a lot of, these CDs have a lot of small, there are tracks on these CDs, and those tracks are made up of some bumps and some, those are called, I think, grooves. There are grooves and there are, there's something else, I mean, I'm forgetting the name. But anyways, so there are grooves which are, which are depressions, and then there are flat parts which are not depressed. So you have those smaller, very small holes in these CDs, in the track over here, and when you shine light, the light would get diffracted because of those grooves, and you would see. So I'll just show you quickly what happens when you do that using a CD. Let me just show you quickly. So here is what happens when you shine a laser on a CD. So again, the setup is very simple. This is a toy laser which you can get easily on a stationery shop. Shine it on a compact disc, and this is what you get. So this is the bright fringe in the center, and then dark fringes, and then again bright spots, and so on and so forth. So pretty simple. I mean, you can create diffraction, and now what you can do is you can even figure out the distance between those grooves using diffraction if you know the formula. And I'll show you, I'll give you a demonstration of that as well. So as you can see over here, if your width is getting smaller, then as you can see that the width has become 0.02 millimeter, then this brighter fringe at the center is becoming broader, as you can see, right? 0.16 millimeter is much larger than 0.02 millimeter. 0.02 millimeter तो बहुत छोटा है. So if it is smaller, if this space between the jaws और ये जो width slit है, ये अगर छोटा है इसका width, तो ये जो बीच का fringe है ये मोटा होता जाता है. This becomes broader. So which is very easy to see if you have a vernier caliper, or if you have wires of different width, or if you have pencil leads, you can also do it with pencil leads. Pencil lead आता है ना 0.5 mm, 0.8 mm and all that. So you can do that using pencil lead as well. So what I'm trying to propose is that you can measure the particle size using diffraction, and let me show you how do we do it. So we have tried figuring out the size of the width of our hair, human hair, using this. So let me show you the demo. So this is a piece of paper जिस पे वो we have pasted the hair, the strand of hair, and then the laser is shining on the strand of hair, and then the laser goes through it, and then it creates a diffraction pattern. I'll just show you the diffraction pattern again. Yeah. So this part. So this creates a diffraction pattern. Now what you can do is you can find out what is the distance, or what is so basically you need to know how far away the minima is. The first minima is from the center. This is the center. How far away the first minima is from this center. And as we can see, this is somewhere around 47, right? This is somewhere around 47, and this is somewhere around 51.5. So the entire, this dark spot to dark spot to this dark spot. So this, from this dark spot or dark fringe to this dark fringe. So if you find out this distance, what do you get? You get around 4.5 millimeters, centimeters, sorry. So ये 4.5 centimeters आ गया, and what you want actually is कि center से जो first dark fringe है उसका distance क्या है? So what is the distance of the first dark fringe from the center? That's what you want. So if the total width is 4.5, then this must be 2.25. So we know now, right? We know this distance from center to the dark fringe. It is 2.25. Very easy, right? And then what do we know? We know how far away our screen is. Our screen is around how much it is? It is 275 centimeters away. So our screen is around 275 centimeters away, right? So हमें पता है कि how far away our bright fringe is. So if you can see this diagram, we know this distance, not this y, but this y. I mean, this is the first dark fringe, and this is the center of the maxima. तो ये जो distance है ये हमें पता है. This came out around 2.25. ये जो distance है d, the capital D, this we know, and we want to find out the width of our human hair. So let me just quickly do this calculation for you. So what do we know? We know that d sine theta is equal to lambda, right? You can replace this lambda by 750 nanometers. 750 into 10 to the power minus 9. Right? Then this sine theta can also be written as, if you have closely observed that diagram, तो ये theta है, बहुत small theta है, तो sine theta and tan theta are same, right? You can approximate sine theta equal to tan theta. So perpendicular upon base could be sine theta. This was 2.25. This was 2.25. And this distance was around 275, if I remember correctly. It was around 275. And this d is the width of the hair, which is what you have to find out. So सब कुछ तो है हमारे पास. You know what is sine theta. You know what is lambda. You can calculate it. And this comes out, and you can do the calculations yourself. You would figure out that this is very close to the width of the hair. So imagine how powerful the diffraction technique is. Right? Does this make sense? How powerful is this diffraction technique? You can actually figure out the width of a human hair using diffraction. कितना simple था ये experiment करना. a very simple formula, right? A very simple formula, just apply it and you can find out the width of human hair. So please try, all of you try figuring out the width of human hair. A lot of people are worried about the thickness of their hair. If the hair are thinner, then they are weaker, or maybe you might have hair fall or whatever. I'm not sure if that is pseudoscience or correct science. I'm not aware of that. But if you are really worried about your hair health, you can do this diffraction experiment and find out the width of your hair, and you can see if it is increasing or decreasing. Such a simple thing to do. Otherwise, it is very difficult to figure out the width of human hair. And similarly, you can figure out width of multiple things which are very, very thin, just by this diffraction experiment. Right? Similarly, you can also find out how tightly woven is your fabric. So if you just shine a laser through your fabric, you would see some diffraction pattern. And that diffraction pattern, if it is if the central maxima is really wide, that means your fabric is very tightly woven. तो अगर तुमको कभी कपड़े खरीदने जाना है, if you want to go and buy, go shopping, then you can have that toy laser with you, and you can just shine this laser. Where did my laser go? Yeah, so basically you can just shine this toy laser on your fabric, and I think you can. Some of our colleagues are doing it. Let me just show you. So you can see this pattern, right? Can you see this pattern? Now this pattern, if it is really far away, I mean, if these bright fringes that you're seeing, if they go real far away, that means your fabric is tightly woven. We have just now read that अगर बहुत छोटा या पतला चीज होता है, और या जो slit है वो बहुत पतला होता है, if the slit is very, very thin, then this fringes, they actually space out, right? And the central fringe becomes broader. We have just now seen that. So you can do the same to figure out whether your fabric is tightly woven or not. So people would argue, this is expensive because it's very tightly knit. So how do we know that? You can do this and you can figure it out. So we can compare two different fabrics and we can see if it is worth paying extra for that fabric which people are arguing are have a better read and pick or whatever. So pretty simple. Thank you, Vijay. So, I'm just saying that diffraction, what we see is not just a concept that you have to learn because it comes in your grade 12 exams. It has a variety of applications in your daily life as well. And if you know about it, nothing like it. Now people have figured out how your DNA looks like using diffraction. I mean, that's what they have done. So you can also figure out the shape of your DNA, the size of your DNA using diffraction. And I'll quickly show you a demo where you can figure out, you can understand what people have done. So what has happened over here is, see, DNA is very small. DNA is just 2.5 nanometers in diameter. So you can't use visible light to create diffraction pattern over here. So what you would need, because visible light is it is much bigger than the size of the DNA. So it would not diffract here, right? So it would not have a considerable diffraction over here. And what does that mean? That means that you would now need something which is much smaller than visible light. So in studies, when they try to find out the structure of DNA, they do X-ray. They basically shine X-ray and then they study these diffraction patterns which look like these, and that's how they figure out that how does a DNA look like. So a DNA has a double helical structure. I'm sure you're aware of it. So a filament in a lamp also has the same kind of structure. So we have repeated the same thing using visible light. You can use visible light for a lamp filament, but you can't use it for a DNA. So let's just use it for lamp filament and see if we get the same pattern. So let me just show this demo to you and tell you. So I just want to demonstrate how easy it is to see this. This is so easy to see and to perform this experiment. So what we are trying to do over here is, we are trying to check if we can ascertain the structure of anything using diffraction. So as of now, our colleague is wrapping this entire bulb with the sellotape because he is going to break it, and when it breaks, it shatters and the glass spreads out. That shouldn't happen. So you should wrap it around like this. I mean, you should wrap a tape around this. So now what you're seeing is just the filament. So the outer glass casing is gone. Now you shine a laser on it. A toy laser again, nothing fancy. And this is what you get. So if you have a structure which is double helix, then you get, which is what DNA is also like, then this is the diffraction pattern that you get. So again, what I'm trying to say is that diffraction can be used, I mean, if you understand diffraction, you can use it to find, you can use it to, probe basic things like whether your fabric is tightly woven or not, and to find out very detailed things like what is the shape of your DNA. Right? So it's such a powerful technique. I mean, if you know about how light behaves, if you know about what diffraction is, there is so much that you can learn. There is so much that you can learn. That's the beauty of it. Right. Okay. So now let me give you a very interesting demo. So because of diffraction. So one thing that I want to tell you is the fact that you do not have color blue. The blue pigment is very, very rare in nature. It's very rare in nature. Jahan bhi blue dikh raha hai, wherever you see blue, it is because of diffraction. It is because of diffraction. So I'll just quickly show you. So can you see some rainbow effect in the, on the slides that I'm showing you? Can you see some colors over here? At least I can see them. Now let me show you what it is. It is just basically two microscope slides, right? These are just two microscope slides, and I have just pressed them really hard. मैंने बहुत press कर दिया उनको अच्छे से यहाँ पे. And what I'm seeing is this colorful rainbow pattern, which you also see when oil film gets spread on a surface. तो भी दिखता है ये, right? तो मैंने बस वही किया है. That is what I've done. And what is happening is something that you can see here on your screen. This is what is happening. Some light is getting reflected from the top surface and some light is getting reflected from the bottom surface, and then they are interfering and they are giving you these multiple colors. That is exactly what happens when you see blue color in stuff like this, in stuff like a feather. Here is your feather. This is a peacock feather. I'm pretty sure you all must have seen it. Now the diffraction is what is causing this blue color, this vibrant blue, to be visible. Otherwise, there is no blue pigment in this feather. कोई blue pigment नहीं है. It is not because of blue pigment. And how do I prove that? So I have this bottle of isopropyl alcohol, and what I'll do is I'll pour some isopropyl alcohol on this. So this is my isopropyl alcohol. I'll pour some isopropyl alcohol on this feather, and we would see that this feather is going to change colors. So you can see the feather, right? Can you see the blue part of it? Let me just place it. Okay, I think some blue can be seen now. Okay, now I would put some isopropyl alcohol in it. Can you see the change in color? The blue turns into green. Do you see that? Why does that happen? That is happening because the color that you were getting was a structural color. It wasn't a color due to pigment. It was because of the fact, and in some time we would see that when this isopropyl alcohol evaporates, you would again get the blue color. The blue color is back. So why is that happening? That is happening because this diffraction, it depends which wavelength is going to ultimately constructively interfere. It depends on the path difference. What is the difference between two waves which are constructively interfering? Now if you add a medium which has a different refractive index, पहले air था, अभी तुमने isopropyl alcohol डाल दिया, it has a different refractive index, so the path difference changes, and you can go back to your theory, your books, and you can figure out why that happens. But you have changed the path difference. When you have changed the path difference, now a different color would constructively interfere, जिसके लिए वो path difference correct है. So instead of blue, now you are getting green to constructively interfere. So it is a very, so people have done this with butterflies. They have done this with peacock feathers, and they find that this must be a structural color. right? Okay. So this is what they have done with a with a with a with a butterfly and a blue color butterfly, and then it turns green if you put alcohol in it. This is the same way by which a chameleon changes its color. I mean, that's the same principle that a chameleon uses to change its color. So what it is doing is it is rearranging its lattice of nanocrystals in one of the top layers of the skin cell. So it has a layer of nanocrystals. You can see these are the layers of the nanocrystals. This and this are those layers. What it would do, it would rearrange these nanocrystals in such a way that इनिशियली जो लाइट डिफ्रैक्ट हो रही है बाद में कोई और लाइट डिफ्रैक्ट होनी चाहिए, क्योंकि जो डिस्टेंस है, पाथ डिफरेंस है, दैट गेट्स चेंज्ड व्हेन यू रीअरेंज दीज नैनोक्रिस्टल्स. This lattice of nanocrystals is rearranged, the distance between them is increased or decreased, and that is how a chameleon, girgit, changes its color, right? So there is so much of diffraction. Now I think there isn't enough time left. Do we have enough time? Can I go ahead with some more stuff? Justy, if you can.
Yeah, Krishna, you can probably take another 5 minutes to conclude.
Okay. So I'll just quickly show you another demo, and this is about why sky is blue. So we have so far what we have done is we have seen that light, most of the times it is okay to believe that light travels in straight line. Also, it is okay. We have seen that there are so many things, there are so many phenomena that are happening around us, which makes us believe that light must be behaving like a wave. And in fact, knowing those phenomena also makes us understand so many other things around us. We can understand how chameleons change their color, or how butterflies change their color, or basically how do peacocks get their color. So now what we are trying to understand is, so there is how does sky get its blue color. So the blue color of the butterfly or the blue color of the peacock feather is something that we understand now. So I would like to, this is the second last thing that I would like to show, that how does sky gets its blue color. And the blue color that the sky gets is because of something called as Rayleigh scattering. Now, why I am showing this, because there is a tendency among students to use the same concept everywhere. I mean, अभी पता चल गया कि blue color peacock feather में और blue color butterflies में is because of thin film interference. So the sky blue must be because of that, or that's how it is. But again, the color blue in the sky is also not because sky has some pigment which is blue in color. It is also because of some interplay of light. And let's do a demo to see how does that happen. So it is called Rayleigh scattering, and I'm pretty sure some of you must be aware of it. But let me just show you how can we recreate that blue sky in your own lab. So this is milk basically, and I'm just putting some milk droplets. Basically, I'm introducing milk protein into water. So water is as of now crystal clear, but now I'm introducing some milk protein in the water. And you would see that as I add more and more milk protein or milk into water, it turns blue. And if I bring in some light source, additional light source from top, it turns red as well. Now I'm not going into details of it, but what I'm trying to tell you is this is a very easy experiment to perform. You can do it very easily at your place. You just need a jar of water and then maybe some milk drops, and then you can check and you can try to understand why sky is sometimes blue and sometimes red. We have done the demo for you, so it could be an assignment today that you now need to come up with a theory after doing this experiment, that why is the sky blue at times and it is red at times, right? And there is one other very interesting thing that happens when this is happening, Rayleigh scattering is happening. There is this polarization that is happening of the light, and that is exactly how honeybees or bees in general find their path when they are lost, because honeybees are so small, they do not have a lot of cues around them. It is all green around them and they are very tiny, so they actually look at the sky, and using the polarization of the sky they can figure out their path many a times. I mean, there must be other cues as well, but they can also take polarization of sky as a cue. So very interesting. I mean, you should try to find out how do honeybees find out their way back to their hives. when they are out. Now I would like to conclude with with something with Raman effect, or with the story of our of a famous scientist from India by the name C.V. Raman. So Raman effect was basically, so what we have seen just now in the case of sky is called Rayleigh scattering. Rayleigh scattering is, so what is scattering primarily? Scattering is when light falls on very small molecules which are even smaller than the size of the wavelength of the light, and then this light, because it's an electromagnetic wave, it excites those particles, and those particles then re-radiate light. Now most of this re-radiation is elastic, which means जो color गिरता है वो का वही वापस आता है. Whatever color you throw, the same color comes back. But very very small amount of it is inelastic. Very very small amount of it is inelastic. मतलब तुमने color कुछ और फेंका, you have thrown some other color, and the color that comes out of those vibrations of those atoms and molecules is something else. It happens 1 in a million times. So out of million tries, you would get just one different color. And C.V. Raman, a scientist from India, was credited to discover this phenomena. And if I tell you the story of C.V. Raman, you would be astonished. I mean, he was completely studied in India. I mean, he did not go to any abroad fancy university, and it was in 1920s when he did his discovery. Even before than that, so hardly, I mean, maybe there were facilities, but not as good as anywhere else. And we were definitely under British control. So those were the days when he was studying it, and he was studying a phenomena which was so rare to observe that it happens 1 in a million times, but he was still able to see it. And the reason why I'm sharing the story of C.V. Raman with you is I want you to appreciate how does the beauty of scientific method. So with C.V. Raman, what happened? He was able to use some filters, and he was able to filter initially the violet light, which is the famous Rayleigh, the light that you get in your sky, right? The blue light. So he was able to get that. The blue light now was falling on some liquid, and the liquid was re-radiating some other light. That some other light was once in million trials was not blue. Once in a million trials was not blue. So, and he was able to filter that also using some green filter. And he was able to figure out that, okay, sometimes I get, using this green filter also I get some light, which means, I'm getting green light as well, or some other light as well. So the point that I'm trying to make is that this is what science is. Science is that you believe in something, you have a hunch for something, then you create an experiment, and you rigorously keep doing this. You keep doing those experiments, keep performing those experiments. Even with C.V. Raman, who had so little resources, and this was, this observation was a qualitative observation. He had to quantify it. So to quantify it was even more difficult, because somebody might say that तुमको green दिखता है, मुझे नहीं दिखता, I don't see that green color. So you have to actually measure that wavelength and then report it. And then it was by an Indian scientist who is hardly known abroad. So it is like winning an F1 race using a Maruti 800. So that's what is the effort that people have made in our country. And by this story, I just want to inspire you, and I want to tell you that such things have happened back in 1920 or even before. It can even happen today. I mean, he won, of course, the Nobel Prize for his discovery, which is called the Raman effect. So I would conclude by the story of C.V. Raman. I hope you read more about C.V. Raman and get inspired about science and about way things are being done in science. Okay, thank you so much. I hope you learned something out of today's session.
Thank you so much, Krishna. Thank you to entire team of IIT Gandhinagar. Students, do we have any questions or any queries? If not, then we can conclude the session. Any school with any questions or queries? All right, I believe there is none. I'd like to take this opportunity to thank all the stakeholders that are behind the Sparkle Series session, IIT Gandhinagar CCL team for conducting the session, for all the support of Navodaya Vidyalaya Samiti and Department of Science and Technology. With that, I'm signing off. Keep asking questions, keep being curious, and keep falling in love with science. Bye-bye. See you in the next session.